All right, we've now finished talking about the different ways for testing series for convergence and divergence. We've talked about the integral test, the comparison test, the alternating series test, absolute convergence, and the ratio and root tests. And so now what we're going to do is, similar to what we did for integration, we want to think about how to approach if we're just given a series, a random series with no context. So we're not in a specific section or anything like that. And we need to be given that random series and decide how to test it for convergence or divergence. Which one of these tests do we use? And so we could just go in order, start with the integral test and work our way through, but that's not efficient. That's you don't want to do it that way. And so what we're going to talk about in this video, we're going to go through section 11.7. We're going to talk about a strategy that we can use for convergence testing. And then in the next video, we're going to work like around 40 convergence testing problems, right? Just random, we're going to be given a random series, and we need to find out if that series is convergent or divergent. Okay, now before we get into this section, I want to note this again. I've mentioned this already before, but you might be thinking that with the tests that we've learned, it might not seem like it's that much. To where like we can only test with the tools we have, we can only test a limited number of series. But remember, in actuality, it's the opposite. With these tools, we can test a large percentage of series, if not all potential series. Well, I don't want to say all. There could be some special kinds of series, but a very large percentage we can test with just the tools we've learned. And the reason is because the error you're making in your head, if you're thinking that we're limited, is that, so like, you're thinking we're limited because, for two of these tests, we can only deal with positive functions that were decreasing. Okay. Well, I already talked about a positive function that's decreasing, that those tests also apply to a negative function that's always increasing, because you can just take out the negative sign and put it in front of the summation, and then you have a positive function that's decreasing. But really the main point is that, so yeah, around the origin, for any function around the origin, or say like around from minus 100 to 100, let's say, functions can do all kinds of things, right? They can, you think about high order polynomials, they go up and down, they do all kinds of things. But remember, all we're really concerned about, all of these tests, you can pick any n value starting at whatever, and as long as going from n to infinity, the function obeys the restraints of these tests, like it's always positive or decreasing, etc. Then you can run the test for the series. Well, when you think about all the functions you're familiar with, and you strictly think about how they behave going off to infinity, the behavior is much more stable and predictable. It makes a lot more sense that when you think about it, a lot of the functions that you're familiar with, when you think about going off to infinity, they're either always they're monotonic increasing to infinity, or if they have a horizontal asymptote, well then as they approach that asymptote, they're just monotonic decreasing, always positive, right? So when you think about strictly, we're thinking about as the function goes off to infinity. Well, then now when you think about it from that perspective, we can test the overwhelming majority of series that are based off of the series that are built off of like functions that we're familiar with from algebra and trigonometry, etc. Okay. So, all right. It says we now have several ways of testing a series for convergence or divergence. The problem is to decide which test to use on which series. In this respect, testing series is similar to integrating functions. Again, there are no hard and fast rules about which tests to apply to a given series, but you may find the following advice of some use. So it is not wise to apply a list of the tests in a specific order until one finally works. That would be a waste of time and effort. Instead, as with integration, the main strategy is to classify the series according to its form. All right, so here are the suggestions they give. If you're, what do you do if you're given a random series with no context? How do you test it? Well, the first 2 points are obvious. Look and see, is it a p-series or a geometric series? right? And so specifically with geometric series, you might have to do some algebraic rearranging first to identify that it is in fact a geometric series. But in general, if you can identify that you have a P series or a geometric series, well, then we know how those behave. In fact, with a geometric series, we're not even going to do a convergence test. We actually, if it converges, we actually know the value of what the series is, right? So it's not even like really convergence testing. We actually can get the S sub n formula. With a P series, we don't get the S sub n formula, but we just see as P greater than 1, then it's convergent. As P less than 1, then it's divergent. All right? So the next tip is that if the series has a form that is similar to a P series or a geometric series, then one of the comparison tests should be considered. All right? So, okay, in particular, if A sub n is a rational function or an algebraic function of n, and what they mean by algebraic function is that it involves roots of polynomials, then the series should be compared with a P series. Notice that most of the series in exercise 11.4 have this form. Okay, so let's go take a look at the exercises from section 11.4. Okay, they're talking about, so most commonly they're talking about rational expressions, rational functions, and so what they're saying is that, like, if you have a rational function, let's say that's the series A sub n, then you want to really consider doing a comparison test with a P series. So where are some rational functions? Like, here's a rational function. So we worked a bunch of problems like this, and we worked all these odd number problems, but what did we do here to test this? We compared this to this P series, right? Because we knew that, because we could easily say that this was always less than this. So since this was convergent and always greater, then that meant this was convergent. And so what they're saying is with any rational function, you can come up with a P series to do a comparison with. Or I don't want to say any, but most of them, right? This was a simple one, but even, like here's one that's not quite as simple, but it's the general idea is, what you can think about is you take, like, your comparison is going to be the order of the numerator divided by the order of the denominator. So here that was 1 over n cubed. Here that would be n over n cubed, so 1 over n squared. Well, so the way you think about that is, so n over n cubed. And as n goes to infinity, this 1 and minus 1, positive 1 and minus 1, you don't have to think about those anymore, right? And so with comparing n over n cubed, this here is always, that's actually this one's kind of difficult because you subtract 1 from the numerator and then you also add 1 to the denominator. So this will take a little more analysis, but you should be able to do this comparison here. This should be that as n gets larger, I forget how it would work, but I'm pretty sure I don't know the specifics of this problem, but you would start by doing this comparison, n over n cubed, which is 1 over n squared. You would bring in that for comparison. And so when they talk about algebraic functions, though, they just meant, like, they're saying when you have a root over a polynomial, so you could still do, like, look at this and bring in a P series. What you would do here is you would say, so the order of the numerator is k to the 1/3, and the order of the denominator is k to the 3/2. And so then we did this problem. You do 1/3 minus 3/2. I think that's 7/2 maybe, or it's minus 7/2. So you get 1 over k to the 7/2. That's a P series with P greater than 1, and you do a comparison there. I forget exactly how this ended up working out, but that's what we did. Here you would do a comparison with 1 over the square root of n squared, so 1 over n. Okay, so rational functions are what they're calling algebraic functions that involve these roots like this. You compare it to a P series, or that you consider doing that. And you might be saying, well, does it have to be a ratio? Well, okay, if you had a polynomial that wasn't in a fraction, or even a radical that wasn't in a fraction, but like it was a radical of a polynomial, well, that series is not going to converge, right? If you just have a sum of a polynomial, then think about it. That's not going to converge, right? And same thing if you had, any kind of a radical of a polynomial that's not in a fraction, that's not going to converge, right? Okay, but it also says you want to look for forms that are similar to not just a p-series, but to a geometric series. So we did a bunch of these as well. Like here, we could take out the 1 and say, so 6 to the n over 5 to the n is 6 over 5 to the n. And so now if we we just took out the 1, so that means that this is always less than this. Oh, no, it's the other way, -1. So this is always greater than this. And so this is divergent, right? This is a geometric series with the common ratio greater than 1. Well, since this is always less, then that means this is divergent. So you want to think about geometric series as well. And in other words, if you can make a simple change to the a sub n to where you get a geometric series, and then you could easily see that the geometric series you brought in is either always less than or always greater than the main series, the main a sub n. All right, the comparison tests apply only to series with positive terms, but if the series has some negative terms, then we can apply the comparison test to the absolute value series and then do the test for absolute convergence, right? So yeah, remember that. Yes, the comparison test, the integral test and the comparison test were restricted to only positive series with only positive terms starting at some n value. But when you think about the idea of absolute convergence, you can still take the absolute value, like do the series of the absolute values and do the integral test, the comparison test. And if it converges, then it's absolutely convergent, which means it's convergent. Okay, here it says, so yeah, if you can see at a glance that the limit of the a sub n is not equal to 0, then the test for divergence should be used. Yeah, so you always want to look at you're given a series, take a look at glance at the a sub n and think about its limit. If it's obvious that the limit of the a sub n is going to diverge or it's going to converge to something other than 0, well then just do the test for divergence. Because you know it's going to diverge. Okay, now number 5 is, this is a one that you forget when you first start working these kinds of problems. Whenever you see an alternating series, if you're given an alternating series, well then obviously one of the series you should strongly consider is the alternating series test, the test that has the name alternating series in it, right? But it's not like with every single alternating series you have to use this test. Where there's other tests you can do. Right? You could always take the absolute value and do a test for absolute convergence. Take the absolute value and do a comparison test, or like the ratio and the root tests are based on the absolute value as well. And so you could use those with an alternating series. But still, for any alternating series, the first one you should think about is the alternating series test. All right, series that involve factorials or other products, including a constant raised to the nth power. So a constant raised to the nth power is like 2 to the n, or e to the n. Factorials, or a constant raised to the nth power, are often conveniently tested using the ratio test. Okay? So it's not like, if we come back here, here's a test with a factorial that we did a comparison test with. So these aren't these are just suggestions. But in general, when you see a factorial, you want to think about the ratio test. Like even here, this looks like it would be great for the ratio test. I'm not sure if it would work, but it looks like it should work great. Right? Think about this. So n plus 1 factorial is n plus 1 times n factorial over n plus 1 to the n plus 1. So n plus 1 times n, so like that, right? Times, and then we would have n to the n over n factorial. So you've got n to the n over n plus 1 to the n. So n over n plus 1 to the n. As n goes to infinity, you get 1 to the n, so 1 to the infinity, that's an indeterminate form. So, I mean, I'm not going to keep doing this, but that's an indeterminate form. We'd have to keep going, but, still, we know how to solve an indeterminate product limit, right? You could do like a logarithm, and that seems like it worked just fine. But whatever that limit is going to tell you if it's absolutely convergent or if it's divergent. Unless it's equal to 1, then it's inconclusive. But I'm just saying we also we obviously solved this using the comparison test. Okay, so powers, and they were actually saying we just evaluated one with n to the n, but they were really saying a constant to the n. But still, in general, powers like this or factorials are both multiplied together. They're saying they're the products of these types of terms. Consider the ratio test. Now, a good note here that they mention is it says, bear in mind that a sub n plus 1 divided by a sub n, as n goes to infinity, is equal to 1 for all p series, and therefore all rational or algebraic functions of n. Thus, the ratio test should not be used for such series. So they're saying, p series or functions that are similar to p series, right? So like these are similar to p series, and we showed why, because you can, this is really a p series, like n over n to the, so 1 plus 1/2 is 3/2, n over n to the 3/2, that's a p series, right? Well, you got n plus, just adding 1 here, this is extremely similar to a p series. It's not an actual p series, but it's very similar. And that's why if you did the ratio test, then the limit of a sub n plus 1 over a sub n, the absolute value, is going to go to 1 for all of these, for most of these. That's going to be the case, which that's inconclusive with the ratio test. Okay, if a sub n is of the form b sub n to the n power, then the root test may be useful. Yeah, so this one's the most obvious, I think. If you see any sequence inside a series where the sequence is everything is raised to the n power, well then yeah, consider the root test. All right, if a sub n is some function of n where you can look at it and see that if you replace the n with an x, you have a function that you could easily evaluate this integral, 1 to infinity, then consider the integral test. However, there are restrictions. It needs to be positive and decreasing from 1 to infinity or from some n to infinity. All right, so they give some examples here that they don't work these. They don't do the full convergence test. They just state which they're going to use first to try and solve it. But okay, here is a rational expression. So we think about the comparison test. Definitely not the ratio test, right? Think about I'm sorry. They look at this and they notice immediately that this limit, the limit of this a sub n, is, if you remember from limits, you can look at this and see the limit of this a sub n is going to be 1/2. Well, that's not equal to 0. So this is going to diverge based on the test for divergence. All right, here, they call this an algebraic expression. It's not technically a rational expression, but it's close. It has a radical, but here you do the comparison test, and you would use, so in the numerator, you've got n to the 3/2. In the denominator, you've got n cubed, so 3/2 minus 3 over 1 is 6. So 1 over n to the 3/2. You bring this in for a comparison. This is a p series that's divergent. P is greater than 1. You bring that in to compare. Okay, here they notice that you can replace n with x, and you have an integral that you can plug into the integral test, and it's decreasing, so it applies to the integral test. But you can also, you see, it's a product of like a power of e, and so you could also in n, so the ratio test also works. Here, alternating series, so the alternating series test. Here we've got the factorials and powers, so ratio test, right? Here you can compare this with a geometric series, 1 over 3 to the n, so 1/3 to the n. So a comparison test where you're bringing in a geometric series. All right, so now we're going to work all of these problems in just like random order. So you can, and that'll be it for series testing.